Hi, Andrew.
Oh, I was muted. Hey,
How are you?
good. How's it going?
Not too bad, not too bad.
Nice.
Nighttime here.
Oh, yeah.
Yeah. So it's deep night in Sweden at this time of year at 6 p.m. It's been night for like 3 hours. It's kind of crazy.
Hey,
Oh,
Rodrigo.
oh dear.
Hi, how are you?
How are you?
Good, good. Should I just quickly try my
Yeah, let me, I just need to open up screen sharing.
Mhm.
Okay, should be good now.
I'll be right back.
Should I go ahead?
Yeah, go ahead. Okay, yeah, we can see the slides. So if you want to go, I don't know, into presenter view.
Okay.
Yeah, that looks great.
All right. That's good.
Do you have a preference on going first or second?
I'm fine.
Okay,
Whatever the other person prefers.
great.
So
How's
we
everything been
so
since you left Seattle, Rodrigo?
what's that?
How's everything been since you left Seattle? It's been like a month.
Oh, it's been great. Been good.
Yeah.
Yeah, busy, somewhat busy, but yeah, good. Um, what was I gonna say? So there's only two of us.
Yeah.
Yeah. So do we get a bit longer or?
Yeah, so I mean, basically, probably like 15 to 20 minutes if you need it.
Mhm.
But also if you just have the normal AGU
Yeah.
length, which seems
Mhm.
to just be getting shorter and shorter, then there'll just
Yeah.
be time for
Yeah.
discussion.
Yeah.
But yeah, if you want to take,
I have,
15 or
I haven't actually timed it, but I'll try and go through it as quickly as possible. Yeah, it's a bit of a complicated story I'm trying to tell. So
yeah.
this particular talk, I always find I go over time. So anyway, it's good. I'll try to get through it in good time, but it's good. There's a bit of a buffer.
Yeah, so I'll probably give you, I don't know, if in that case I'll give you 2 minutes for 20 or
All
so.
right. Mhm.
Does that sound good, Andrew?
Can you say that again, Matt? I wasn't
When
really
there's only
listening.
two, we say like maybe 20 minutes is fine, right?
Yeah, I mean, it's if you don't need that much time, that's also
Right.
okay.
Yeah.
But
Okay. Yeah.
um,
I'll try to keep it short.
yeah.
Yeah. And here's Lori.
Hey, Lori.
Hi, can you hear me?
Hi, Lori. Yeah, we can hear you.
Yep.
Okay, and you can see me now, right?
Yep.
Okay, good. I had to use my personal computer because the government one never lets me do audio or anything. So
Yeah, I've dealt with some I'm partially at NOAA PMEL and to try to do Zoom meetings with my advisors, we've just given up and done Google Meet now.
yeah,
Yeah.
yeah, I almost get when it's virtual. I'm like, but yeah, I'm
Do you want to quickly try to share your screen? And I opened up
glad it's
that.
working. Can you talk?
Lori, do you want to quickly share your screen and make sure we can see your slides?
Yeah. I'm sorry, it was cutting out briefly there. I hope my Wi-Fi is okay too. Yeah, I'm gonna pull up my slides right now.
Perfect.
They're very slow to load here. Okay. All right, and then share.
Yep.
Um, do I do entire screen? I'm used to Google Meet.
Yeah, just share. Probably if you have only one laptop screen in front of you, probably entire screen.
Okay.
It's still loading up for me.
Yeah.
Okay.
Yeah, that
Going?
looks good. Yeah. Although
Okay, so
I think
since I haven't, I
go
was gonna
ahead.
say, since I haven't been in the forum before, how do you handle like questions during the talk or?
So generally folks put stuff into the chat during the talk. But at the end of the talk, you know, questions will be open and pretty much we'll either ask the folks who ask the questions to just ask you directly and unmute, or they can raise their hand and unmute separately. But generally folks don't ask questions during the talk.
Okay, just because right now I only see my slides, so I can't see if anyone's asking question.
Yeah. But basically I'll be paying attention to it, so I wouldn't worry too much. So if something were to happen, like, you know, your screen wasn't showing, I would just let you know.
Okay, so right now all you see is my screen, right?
Yeah, that's right.
Yeah.
Okay, and I can't see a chat. Okay, I just want to make sure.
Yeah, it's okay.
Do you have a do you want to go first, Lori? While we're pulled up.
Or I
I'm
have
sorry,
the
can you
intro
repeat that?
slides to go through as well.
Oh, sorry, Andrew has the intro slides. That's right.
Yeah, I'll just read.
Okay, great.
Sharing.
Can you stop? Yeah, if you stop sharing for a second, Lori, I'll bring up my slides.
Yeah, sure. Yeah.
Um,
Oh, I hit stop sharing, but
Cool.
it's saying
Yeah,
high
you-
CPU usage.
oh,
Did it stop sharing or?
yeah,
Yeah.
it stopped sharing, but you're cutting out a little bit. But
Oh, okay,
hopefully,
good.
hopefully it'll be okay.
Yeah.
Okay.
Let's stick with it for a second. All right, we'll give people a couple minutes to join. So.
So everyone had a nice Thanksgiving?
Yeah, it was a relaxing weekend.
Good.
Yeah, ate a lot of food, slept
Yep.
a lot. It was good.
I'm going to AGU, so I was trying to get all Christmas stuff done quick.
Oh, at least AGU is close this year.
That's why I was going this year, because I'm like, okay, it's close and you know, I can hack it, but I'm missing a few concerts for my kids, but you know.
Oh. Rodrigo, do you want to go first? Because maybe, and then Lori, or does anyone have a preference? Well, no.
I don't have a strong preference. So
Neither
Okay.
do I.
Okay, well, I've got Lori down as first. Actually, we'll stick with Lori first, and then
all right,
Rodrigo.
that's good.
So I don't have to change the slides. Cool. All right, we've got a steady number of people, so let's get going. So yeah, welcome everyone to the 39th Climate Sensitivity and Cloud Feedback Virtual Symposium. And today we got two speakers. We got Lori Sentman from NOAA GFDL, who's going to talk to us about impact of atmospheric chemistry and composition on climate sensitivity. And we've got Rodrigo Caballero from Stockholm, who's going to talk to us about polar lapse rate and radiative-advective equilibrium. Where's the thing? So if you haven't been to this symposium before, today we're going to have 2 short talks. Because there's only 2 talks, we'll give you a nudge at say after 15 minutes or something. So there's no need to be strict on time today. It's at Matt's discretion, whatever he wants to do. We'll be chill. Save your questions until after the talk. You can put stuff in the chat if you want, or we'll unmute you after the talk. You can ask the question yourself. We have a lot of people who work behind the scenes on these things, and then we have a lot of backup or previous talks if you want to go and see them as well. And one final slide is we're thinking of doing something like this in person at EGU. So, this community has been meeting virtually for the better part of 4 years now. And a few of us were talking, and we realized that EGU doesn't actually have a climate sensitivity session. So a few of us have proposed this session, climate sensitivity, radiative feedbacks, and the pattern effect, focusing on radiative feedbacks, ocean dynamics, clouds, ocean heat uptake, theoretical insights, teleconnections, things that are very relevant to this community. And so we've got Yenting Huang from National Taiwan University, who's going to give an invited talk. And so we would really like to have as many people as possible from this community joining if they can. And yeah, the deadline for abstracts is 15th of January. But if you want to also apply for travel support, if you're an early career scientist, or there are certain restrictions that they have, but you can look into that. The deadline is today, so I thought I'd give you a heads up. Anyway, enough from me. Lori, do you want to share your screen again and take it away?
Okay, sure. Okay. I have a little lag there, so let me know when it shows.
It's showing Zoom, yeah.
And okay, are we good?
Yeah, it looks good. There's a little bar in the middle. Maybe if you want to, can you see that?
Oh yeah.
Do you want to just hit hide? Yeah.
Yep.
Great.
Okay, very good. Okay. All right. Well, yes. I want to thank, both Matt and Andrew for inviting me to present research. In fact, I didn't even know about this forum. So, I'm excited to hear about it, and, hoping I can, join in on more talks in the future. But my role at GFDL is basically using Earth system models to study climate carbon feedbacks and interactions. So I do that on a range of time scales. I've done paleoclimate studies with idealized simulations to many cycles of CMIP, present and projections, and now using TCRE for ESM to drive the model, with emissions for target warming, to study offshoots and global warming levels, stabilizations, and so forth. So just a little background on me. That's kind of my past, but I also have, I would say, inherited, when I started working with Ron Stauffer many years ago at GFDL, the slab ocean model. And that was from Mike Spellman, and that dates back to early 2000s. So maybe I'm dating myself as well, but, so I've done slab ocean model and then Earth system models. So, this hierarchy of models, and it sounds like it's all over the place, but I have to admit that I really got an appreciation for the different models and their hierarchy and what all of them can provide. So basically today I am going to kind of tie all that in together. I'm going to use slab ocean experiments that we've done at GFDL to study different model representations in our Earth system model and to see how they impact equilibrium climate sensitivity. So that's just a background. And I know this forum, we know a lot about climate sensitivity, so I don't really have to go into, the details here. But, we know that the main question is how much the Earth is going to warm if CO2 is doubled. And this is a key metric that we use. And I find one thing I want to mention is I find that it is pretty fascinating that our range really has not changed much, over all these years of model development, even though we've narrowed it quite a bit. And I think that really tells a lot about what we're trying to get at when we're looking at climate sensitivity. And I was talking to Nadir at my lab as well a little while ago, and we started talking about, okay, we have all these different metrics, climate sensitivity, and, and everybody's worried about this number, and what does this tell us? And, it just really makes you think of like, what are we trying to get at with this? So in doing a lot of these studies over these years, the main thing to remember is that, equilibrium climate sensitivity estimates vary across models and calculation methods, but a lot of the uncertainty arises from the climate feedbacks in the system. And I think that really is what we should kind of constrain or aim to constrain in our studies of climate sensitivity, as well as, of course, narrowing the range, which is important. But so I just want to mention that this is where kind of, my evolving of climate sensitivity and my work has led me to. So, and I don't know if any of you have met Suki Manabe, but he is obviously a major pioneer of using slab ocean models to estimate equilibrium climate sensitivity. Again, that's the one metric I'm going to be talking about today. But he was the mentor to my previous supervisor, Ron Stauffer. And one of Suki's big sayings was simplify the model and you will have great things. I remember him saying that. And, and he's absolutely right. There's a lot that can be said from going from state-of-the-art comprehensive models to simplified models. And again, this hierarchy of models, I feel, is very important. So going back to my history at GFDL, I've been involved in developing our slab ocean model since back CM 2.1. So we're talking the early 2000s and going through different cycles of CMIT. And in doing so, part of my, duties was to do, the pre-industrial control simulations, the 2X, calculating ECS. And it really just kind of took me a while to get an appreciation for why I'm doing this and what is it telling us. And I think mainly recently, it really kind of made sense when we started developing our 4th generation coupled models at GFDL. This was pre-CMIP 6. So we're talking our coupled physical model, which is CM4. And that is based on our first chemistry climate model, CM3, and also our first, or our ESM 4.1. It's based on our first Earth system models at GFDL and NOAA, which was the 2-class model. So ESM 2M 2G. So I know I'm giving out a lot of acronyms here, but basically we've been developing our newer models, CM4 and ESM 4.1. These are our physical climate model and our Earth system model. And these were major contributions to CMIP 6. So in doing that, I developed the slab ocean versions of these models, and with the different applications, one of which, of course, was to estimate the equilibrium climate sensitivity, which I've done, for many model generations. And in doing so, we found that there was a rather significant difference in our ECS between CM4 and ESM 4.1. In fact, it was 0.7 degrees. and CM4 had a higher equilibrium climate sensitivity than the Earth system model. So the advantage was that since we developed these models based on previous versions, there were some components that were actually similar. And this way we were able to kind of key in a little more on what the feedbacks were that maybe contributed to this difference within our own model versus a model into comparison that we see a lot with ECS estimates. So this table here shows basically like a high level depiction of the different components between CM4 and ESM 4.1 as they relate to our slab ocean model. So of course there's differences in the ocean, but for the slab model, we replaced our MOM6 ocean with the simple mixed layer model or a 50-meter slab. So one of the big differences between the two models is the atmospheric component. CM4 is based on AM 4.0. And while the horizontal resolution between that and the atmospheric component in ESM 4.1 are similar at 1 degree, ESM 4.1 development focused more on increasing the vertical levels in the atmosphere, and this allowed us to better resolve and represent dynamics, especially stratospheric and chemistry dynamics in the atmosphere. So that was the main focus of ESM 4.1, while CM4 focus was better resolution in the ocean component. So now that we're kind of neglecting the ocean here, we can kind of focus on the atmospheric component differences. There also is differences in the land components. We have LM 4.0 and CM4, and in ESM 4.1, we have an updated land model, LM 4.1. And a lot of the differences basically have to do with land use representation, perfect plasticity approximation, competition among trees, and then the sea ice simulator or sea ice component is the same between the two. So just to give you an overview of the differences, we estimated the ECS, like I said, between the two models using our slab ocean model. And in doing so, we do 200-year idealized experiments. So we have a couplet. We have the 1x CO2 based on pre-industrial CO2, and we have our 2x. And for each of these, we find that the CM4 has a higher equilibrium sensitivity. And then here, just a little background, I don't want to go into too much detail, but we drive our slab ocean model with heat flux adjustments. This compensates for the lack of horizontal transport and heat in the slab ocean model. And we also, since it includes the carbon cycle, there's long time scales, especially with our land component with the dynamic vegetation. So we accelerate soil carbon spin up offline, just so that, we make sure that we are at equilibrium when we do perform these experiments. Okay, so this just basically shows the ECS that we estimated using our slab model between the two. And, just want to note, going forward, the red will be ESM 4.1 and the blue is CM4. And then you can see that, we are within the range, of course, of estimates, even though that range kind of, was always kind of evolving. But our estimates are very consistent, though, with estimates provided by a paper in 2020 by John Dunn and others, where they use the full ocean couple models using the Gregory method and different timescales and different metrics to compute ECS and TCR. And in that study, it also showed that CM4 had a higher climate sensitivity than ESM 4.1. So the point is that this has been consistent among many different studies. So going to the gist of the talk basically is, between the two models, we kind of hypothesized during development of, hey, what could cause this difference? And the first thing that really kind of jumped out at us was mainly the difference between the physical climate model and the Earth system model. Again, these climate feedbacks really play a part in the uncertainty in equilibrium climate sensitivity. So we identified 5 potential drivers that were different between the models, and that we assumed could cause climate feedbacks, and that could cause this difference. And they mainly were related to aerosol representation in the model and interactive ozone. So to quickly kind of summarize, the 5 of those included stronger temperature dependence of sea salt emissions in ESM 4.1. So we replaced the sea salt emission scheme with one where it was dependent, had a stronger temperature dependence. So we obviously, emitted more sea salt emissions in the model. The other one is that ESM 4.1 included a sea ice mask. And what this did was mask the marine aerosols and prevented them from going to the atmosphere. And this kind of is a complex feedback, but we hypothesized that this could potentially be a negative climate feedback in the ESM. Also, we have interactive BVOCs in the ESM 4.1 that we don't have in CM4, and interactive stratospheric ozone. And there's a lot of literature by NOAA and others that show that the interplay between tropospheric and stratospheric ozone and its interaction temperature dependence does have a negative climate feedback. And finally, the source areas of dust emissions. Since we have interactive dust emissions in both models, the source areas are different between the 2 models. And in ESM 4.1, they are a little more modulated through the dynamics than they are in CM4. And we feel that all 5 of these model differences that are included in ESM 4.1 are negative climate feedbacks. And all of these contribute to that 0.7 degree lower ECS that we see in ESM 4.1 compared to CM4. And the nice thing about this, again, this experiment design, is that this is within our lineage of model development. So we do know our models, we do know what's different, and it's kind of a cleaner assessment of determining the contributions. So in addition to the 2 slab ocean experiments we did with the ESM based on ESM 4.1 and CM4, we ran an additional 6 experiment couplets, 1x and 2x, based on ESM 4.1. In 5 of those, though, in ESM 4.1, we replaced each of those individual factors that I just discussed with their CM4 representation. So basically, we reverted ESM 4.1 for each of those factors back to their CM4 representation. And then in the final experiment, the 6th set, we did the combination of all of those to see if that actually, was a sum of those or if it made a contribution. And again, of course, with the ECS, we focus on a 20-year average between years 61 and 80. This table basically summarizes everything I just said. But this, on the left-hand side, you see the different simulations and the nomenclature I'm using. So we have our ESM 4.1 slab model, and then we have all the ESM 4.1 slab models minus each of those feedbacks. So minusing means that we revert ice mass back to CM4. We revert dust back to the CM4 representation. And this kind of gives a little more background, like I said, into what those differences were. And then on the right-hand side, each of those, as we revert to CM4, that reversion we hypothesize is a positive climate feedback if we go back to CM4. Okay, so I hope that wasn't too confusing. But so just to give a background here, this is our baseline surface climate. So this is the pre-industrial 1850 control runs. Red is ESM 4.1, blue is CM4. And you could just basically, from here, just showing there's not much difference between the 2. CM4 is slightly warmer, but really nothing significant. And, we do have equilibrium in the baseline climate. And here I add the additional experiments again in ESM 4.1, but changing each of those parameters individually back to those CM4 representations. And you can see, other than basically the SSA, which is the sea salt aerosols, and all, which is the combined effect of all of them, everything else pretty much in the baseline climate is pretty similar. And then this is similar to the other plot. This is the response to the doubling of CO2. As you expect, temperatures increase and CM4 increases more. Again, that's why we have higher climate sensitivity. But when we add the other experiments in here, this gives us a little more idea of where these fit in with that equilibrium climate response. And again, from this plot, you could basically see they all kind of fit around the ESM. And you can see the black line, which is the combination of all of them, really kind of falls in between ESM and the CM4. And then each of those, have a very small contribution.
We got about minutes left, Lori.
Perfect, because this is my punchline slide here. This is basically our result then, leading up to this. These are the experiments, and this is what we computed the ECS from each of those experiments. And the feedback ECS effect basically is the experiment's ECS minus ESM 4.1's ECS. So basically you can see that each of these contribute about 1 to 2 degrees toward that difference in ECS, all leaning toward, heading toward CM4. So they all kind of contribute in some sense, with the combination of all of them really, combination of all of them really, being the majority of the contribution to that difference. So basically our results show that, we have a 17% higher ECS in our physical climate model. And we basically examined individual and the combined contributions of different model drivers to see how much the climate feedbacks contribute to those differences. And we find that each of those contribute about 0.1 to 0.3 degrees to that difference of 0.7 degrees. I didn't get to show the plots because I don't have enough time, but basically the spatial pattern really is polar amplification. So there's not any news there, but basically it's very important that we realistically represent these Earth system feedbacks in our future projections, because individually they may not be enough, but when you have the additive contribution of all of those, they can lead up to at least a degree difference in future climate projections. And that's, neglecting any other kind of contributions that we may have too. So I just want to end there, and thank you for inviting me to present this.
Yeah, awesome. Thanks, Lori. So we have a question in the chat from Tim Del Sol. Do you want to unmute yourself, or I can just ask it?
I can.
Yeah. You want me to mute me?
No. I think Tim will ask the question.
Yeah. So,
okay.
Nice talk. This may be a silly question. It was something I've never gotten straight. Does the equilibrium climate sensitivity depend on the depth of your slab ocean model? I know the convention is to use 50 meters, but do you get a different ECS if you use a 10-meter slab ocean or a 100-meter slab ocean?
In theory, it shouldn't, because in theory, ECS assumes that the temperature response scales with the radiative forcing perturbation in theory. But that is a good question, and we haven't really run our ESS or our slab model with a different depth. But I haven't seen in the literature that really made any kind of difference. But that is a good point and something maybe to look into.
Thanks.
Any other questions from the audience? We probably have time for one more before moving on to Rodrigo. And if we have time after that, we can kind of do an open question. So, Lori, does this tell you anything about like beyond the, like if you had to kind of postulate beyond the GFDL models, does this tell you anything? Do you think that like some of the CMIT models, which probably don't have quite as much complicated chemistry, would that push it one way or the other, do you think, the central estimate?
Yeah, that's a good point. I probably should have summarized with that. That really kind of is, where we're kind of leading with this. This is kind of, as the models are being, getting more complex and all, and we are representing these different feedbacks and different schemes. That is a question going forward. And I feel like, this is, our results apply to our model, but it would be great to see similar studies within other models, to see, and we've compared our results, to other ones with individual factors, and, they are consistent with, what they found, each one of those being negative feedbacks within their models. But I do feel that, this is very important and should really be, considered in our future projections. So I do think there should be more intercomparisons related to this rather than, I mean, like I said, the range is important, but, I really feel like this is where the uncertainty lies. And, as we can represent more processes, I think this will give us a lot more information.
Awesome. Great. Well, there's a discussion happening in the chat about the mixed layer depth. So if you want to check that out, Lori, but if you want to stop sharing, we can move on to Rodrigo.
Okay, sure. Thank you.
Thanks.
Okay, can you see that?
Sweet. Yeah, it looks good. And I'll give you a 3-minute warning, Rodrigo.
Okay, let me just get rid of these little bars here. Okay. All right, so I'm a long-time listener, first-time caller on this seminar series, and it's a great pleasure to be here. So thanks, Matt, for the invitation. I'm going to talk about some single column modeling work I've been doing recently together with Tim Merlis, trying to get a bit of a deeper understanding on polar responses to global radiative forcing. Okay. So to set the scene, then you can think of two limits for atmospheric energy balance. So on the left-hand side there, you have radiative convective equilibrium, in which the atmospheric column is heated mostly by surface fluxes. That drives convection through the column, which mixes the column throughout, mixes the troposphere and leads to strong vertical coupling, and so that the temperature profile is essentially constrained to lie on a moist adiabat. And then this heating that is deposited in the atmosphere by surface fluxes and convection is then emitted to space as long-wave radiation, okay? And lateral advection plays a small role. So this is the classic paradigm that we've all been familiar with since the pioneering work of Manabi and Weatherall in the 60s. And it kind of forms the basic, it's where we get most of our intuition about how climate sensitivity works. When you go to the high latitudes, however, this limit of radiative convective equilibrium doesn't really apply, because in that case, you have the main energy source for the column being lateral advection, so air mass is being brought from the mid-latitudes to the pole. And in this case, the atmosphere is typically warmer than the surface fluxes are weak or downward, and the energy conversion due to advection is balanced then by long-wave radiation. And this happens more because there's no convection mixing the troposphere, the vertical coupling is weak, and so this balance is more of a sort of layer by layer balance. So this is a limit that we're less familiar with. because I guess the poles are kind of small and less, fewer people have looked at them. But it's something that has received attention recently, in particular in a paper by Tim Cronin and Malte Janssen, who find that actually the physics of this regime is quite different from that of radiative-convective equilibrium, and the responses to forcing are also quite different. So in particular, I'm going to look at the response of the temperature structure, so the lapse rate, okay? So in the tropics, as you will all be familiar with, when the Earth system is subjected to sort of global radiative forcing in the tropics, which are in radiative-convective equilibrium, the temperature structure responds by reducing its lapse rate. So you get a sort of a bullseye of warming up aloft near the, just under the tropopause. Okay, whereas in the high latitudes, you have a warming which has the opposite pattern, it's bottom amplified, okay? And this bottom amplification contributes then, of course, to the polar amplification of the surface warming, okay? So whereas we understand, at least to zero order quite robustly why the tropics respond as they do because of the moist adiabat constraint, the question of why it's bottom amplified in the high latitudes is still, not fully understood. And so the idea here is to set up a simple model that kind of more or less captures the relevant physics and try and dig into those physics to get, a bit more insight into why this bottom amplification happens, okay? Okay, so this is the basic model setup. So here I'm going to be building then on the work of Cronin and Janssen, and also later work by Henry et al. Okay, and the kind of model that they were looking at in this previous work, you have a temperature profile. You have a single column with a temperature profile T, and the tendency then of this temperature profile is controlled by three terms. There's a radiative cooling term. There's a turbulent, small-scale diffusion due to small-scale turbulence, which also contributes cooling on average. And then there's a lateral advective heating rate, okay? Now, in this previous work, the advective heating was just prescribed, okay? Because, that's the simplest thing to do. How else are you going to compute it? But I'll argue that prescribing it and then looking at changes in the temperature structure due to changes, for example, in radiative cooling rate due to changes in CO2, adds a constraint which is actually unrealistic, okay? And the argument then, in sort of cartoon version, is as follows. So let's consider the polar cap, which is this sort of thick line, here, which has a spatial scale L, okay? And let's think about some air coming in from the mid-latitude, so it's relatively warm and moist, and it has a relatively high moist static energy H in. And this air moves through the polar cap, and as it moves, it's cooling to space and also cooling to the surface, and then when it exits the polar cap again, it's going to be colder and it's going to have a lower moist static energy H out, okay? And so the rate of energy convergence, so the advective heating rate, is going to be proportional to the difference between H out and H in divided by a time scale, which is given by the sort of velocity scale, the speed at which the typical speed on which the air is moving through the column, and the length scale L, okay? Sorry. So now suppose you increase the temperature of the air coming in, so you increase the energy of the air coming in, then the temperature inside the column is going to be bigger, the cooling is going to be bigger, and so there's going to be more cooling and more energy lost to space as it moves through, and so as it moves through the column, and so the difference between H out and H in is going to increase, okay? So an increase in the temperature of the air going in is going to increase the energy convergence, and that kind of, makes sense and is pretty intuitive, okay? But what we also need to realize is that even if you keep the temperature of the air coming in constant, but you change the CO2 in the column, that's going to affect the cooling rate to space and to the surface, okay? Which is again going to affect the advective heating, so the amount of energy convergence, okay? So the advective heating is not really an externally prescribed quantity. It's something that depends on factors external to the column. That is, it depends on the temperature and moisture of the air coming in from mid-latitudes, but it also depends on processes inside the column. So really, the advective heating can't be, to be physically consistent, you can't prescribe it externally. You need to solve for the advective heating as part of the solution, okay? So how are we going to do that? Well, I'm going to do that in my column model exactly as is written here. So I'm going to write the Q advective term simply as a relaxation of an incoming moist static energy and the moist static energy of the column itself, okay? And I'll just note that here I've written the moist static energy. So this is essentially the moist static energy divided by Cp, okay? And I'm neglecting the potential energy term in the moist static energy because I'm assuming that the air moves isobarically, so it doesn't change height when through its motion in the column, and so there's no convergence of potential energy essentially. Okay, so what I'm left with is essentially the equivalent potential temperature TE. Okay, so basically I'm going to represent advective heating, so the convergence of lateral energy flux, simply through a relaxation to the incoming equivalent temperature, okay? And then at the surface, I'm going to couple to a slab, which has a temperature Ts, and its temperature is controlled by a fixed absorbed shortwave radiation, okay? So there's no sea ice or any more complicated representation of the surface here. I just have a slab, and I assume some albedo, and it absorbs some amount of solar radiation through the, in the annual average, okay? And then there's a sensible heat flux. I'm going to neglect latent heat fluxes because the temperatures are very low, and so these latent heat fluxes are very low. And then there's the radiative flux, which is essentially this is only the long wave radiation, because I'm not taking any complicated I'm not making any complicated representation of shortwave radiation. The shortwave radiation is just what's absorbed at the surface, okay? So I don't have time here to go into a more detailed derivation and justification for these approximations, but if you follow this QR code to the preprint, you will see a much more detailed derivation and empirical justification of these approximations, okay? But for now, I'll just go on and show a test of this model against observation. So what I've done here is I've taken the values of TEN from reanalysis, and I've taken the rest of the model parameters have been fixed to sort of more or less realistic values. And then with those values, I've run the model and obtained an equilibrium temperature profile, and I'm comparing that with the actual temperature profile observed in the reanalysis. And as you can see, you get a actually surprisingly good fit. The shading here shows some uncertainty range due to, that you get by varying the basic parameters. And you see that even for a wide range of parameters, you still get at least a qualitative fit to the temperature structure and also to the advective heating rate, actually, okay? So despite its great simplicity, so I'm neglecting, fractional ice cover, I'm neglecting clouds, I'm neglecting a whole bunch of things that we think should be important for the polar climate. Despite this great simplicity, the model seems to at least capture qualitatively some of the basic structures of the polar climate with some realism, okay? So given that we have some confidence in this model, in the rest of the talk, then what I'll do is I'll ask and hopefully answer two questions. The first being, why is there a climatological temperature inversion in the first place? By which I mean this inversion here, the surface-based temperature inversion that's seen both in the model and in the observations. And how does the lapse rate respond then to changing model parameters, in particular the temperature or equivalent temperature of the air coming into the column, the absorbed surface energy, CO, and the greenhouse gases CO2 and water vapor, okay? Okay, so I'm going to start with the base state, which is, pretty similar to that observationally driven base state solution that I was showing you before. I've simplified it a little bit by just prescribing an equivalent, a TE in, an incoming equivalent temperature, which is based on a temperature profile that has a constant lapse rate. Oops. It has a constant lapse rate in pressure coordinates. It doesn't look like a straight line, but if I had height coordinates here, this thick green line would be a straight line. And then the moisture contribution to the moistatic energy, or the equivalent temperature, is set by a vertically uniform relative humidity. And because of the temperature dependence of the saturation vapor pressure, then TE in is bottom amplified. So there's a bigger moisture contribution near the surface than aloft, okay? And the parameters are set to some default values, which are more or less realistic. And when I run the model with that parameter setting, I get this equilibrium temperature profile, which has an inversion, okay? And the question is, why is there an inversion? Well, I mean, here on the right, I'm showing you the heating rates. And so you have a radiative cooling rate and a turbulent cooling rate. And you can see the turbulent cooling rate. This is essentially sensible heat flux through the column and into the surface. You can see that it peaks near the surface, right? So you can say, well, this big peak here is cooling the surface, is cooling the atmosphere near the surface, and it's giving me the inversion. But that's not really an answer, because that just begs the question of, why is this turbulent cooling rate so large near the surface? Okay, so to get a better answer, you need to go a bit deeper, and it helps to look at instead of looking at cooling rates, to look at actual energy fluxes through the column, okay? So here are the energy fluxes, the vertical divergences of these energy fluxes give me the cooling rates that are plotted here, okay? And the dark blue then is the radiative flux, the long-wave radiative flux, and the light blue is the sensible heat flux or turbulent flux. I've separated the radiative flux into two components. Okay, one component is that fraction of the radiation which is emitted by the surface and goes through the atmosphere without interacting with the atmosphere. So this is the radiation that escapes directly to space from the atmosphere. Okay, and in the polar climate, since it's quite cold and we don't have clouds in this model, and there's not much water vapor, the water vapor window is quite wide, and so there's quite a lot of radiation escaping directly to space without even touching the atmosphere, okay? And then this other line is that part of the radiative flux of the long-wave radiative flux that actually does interact with the atmosphere, and that does have a divergence because it's what's causing the radiative cooling rate through the atmosphere, okay? And then finally, the sensible heat flux is appreciable only near the surface, okay? And the sign convention here is that positive is downward, so this flux is downward near the surface. The radiative flux is upward near the surface, but it's quite small in value. So if you add these two, the total energy flux is actually downward near the surface, okay? So that means that the air that is coming into the column near the surface is actually cooling to the surface, okay? Not directly to space, as happens aloft, okay? So that then leads you to a sort of qualitative picture that looks a bit like this. So at low levels, you have air that comes in with some equivalent temperature T in, which is relatively warm, okay? And as it moves through the polar column, it loses heat to the surface. That energy that is delivered to the surface adds to the energy absorbed from the sun, and it's balanced by the outgoing long wave through the water vapor window, okay? So this part of the energy flux here is kind of a shortcut. It's so the atmosphere, the lower atmosphere, instead of cooling directly to space, it cools to the surface, and then the surface radiates that directly to space, okay? So we call this effect, we've coined this kind of cute term, the surface radiator fin, which is reminiscent of the other radiator fin that Rabier Humbert coined many years ago. Okay, so what's that got to do with the inversion? Excuse me.
And we have about 3 minutes left, Rodrigo.
Okay, I'll try to get through it. Let's assume that we suppress the cooling of the atmosphere to the surface. In that case, the F wind, this direct cooling to space from the surface, is entirely balanced by the absorbed short wave, and then that sets a temperature, a Ts star, okay, which is the temperature such that the Planck emission times the width of the water vapor window balances the absorbed shortwave radiation, okay? So that gives you a sort of a temperature scale, which is relatively cold with respect to the temperature of the air coming in, and the difference between these two is what we call the potential inversion strength, because it's assuming this is smaller than this, it's the maximum inversion strength that you can have, okay? Now, when you actually enable this cooling of the atmosphere to the surface, then this quantity will relax, and so the actual inversion strength that you will observe in the simulation will be less than this. But what we find is that you can predict changes in the actual inversion strength by looking at changes in this potential inversion strength, which is something that you can predict a priori based on just these parameters, okay? So let's look at that. So let's look at how the temperature structure responds to different perturbations in these 4 different parameters, okay? So firstly, if you perturb the incoming temperature, and here I'm just perturbing the incoming temperature as a constant, so I'm just adding a constant to the incoming temperature at every level, which means that the equivalent temperature perturbation, which is shown by the thin line here, is bottom amplified, okay? So this, when I do this, I'm increasing this number, but leaving this number alone because I'm not changing any of the other things, okay? And so I'm increasing the potential inversion strength, and I do indeed by 5 Kelvin, and I do indeed find that the response is one that tends to increase the surface inversion, okay? Now, if I increase Fs, I do the opposite. I don't change this, but I change this, and so I decrease this difference, and I find, in fact, a relaxation of the surface inversion, okay? With the greenhouse gases, what I do is I change this number, I change the width of the water vapor window, make it smaller in particular, so this number becomes bigger, and so that, again, the potential inversion strength decreases, and I again see a relaxation of the surface inversion. And when I add them all together, I see that I have a very large relaxation of the surface inversion and a general destratification throughout the column, okay? So to understand this last part, why is there a general destratification throughout the column? I can look at the total response if I take out the response to the surface heat source, okay? And in this case, it turns out that the response to the change in TE in near the surface exactly cancels the response to the greenhouse gases, okay? So there is no change in the surface radiator fin, and what I then see is simply a relaxation to TE in, because that's what I'm doing. I'm relaxing the temperature. In this model, I'm relaxing the temperature of the column to essentially the equivalent temperature of the incoming air, okay? And so it's not surprising that the response has the same bottom amplified structure. Okay, so just to conclude then, we've identified actually, I've only discussed 2, but there's actually an additional mechanism that I haven't had time to discuss. But anyway, the three mechanisms that we've identified are that the polar lapse rate responds to global radiative forcing, essentially by relaxing through three mechanisms. One is this large weakening of the surface radiator fin. Two is a general relaxation to a bottom amplified perturbation in the incoming temperature. And third, there's an increase in radiative cooling at upper levels due to water vapor. Okay. So I'll leave it there. Thank you so much, and I'll take any questions.
Awesome. Thanks, Rodrigo. Okay, folks, any questions from the audience? Feel free to either put it in the chat or just unmute yourself.
I have a question. It's minor, I suppose, but you in your model, you make the assumption that the flow is isobaric.
Yep.
But when a parcel cools, it will sink to its level of neutral buoyancy, which is at a different pressure. Is this an important fact, or is this something you know and you're neglecting?
Yeah, so I mean, I didn't have time to show it here, but if you look in the preprint that's linked here, we go through you can separate the various terms, and it turns out that you can separate the advective heating rate into various terms due to an eddy flux and a meridional circulation, and it's the meridional circulation that contains the vertical velocity, and that term is actually negligible for the Arctic. Okay, so it's for that reason that we feel justified in neglecting any sinking motion happening within the Arctic. It seems that most of the parcels coming in and out of the Arctic are due to eddy fluxes, right? And since the vertical velocity term doesn't play much role, then we can neglect the potential energy term in the moist static energy.
You put the caveat in the polar regions. Would this be true in the mid latitudes?
Probably not. I mean,
okay.
We do have a ferrule cell that's stronger. It just so happens that the Arctic doesn't have a very strong subsidence, right?
Okay, thanks.
We have a question from Eric DeWeaver in the chat, if you want to unmute.
Oh yeah, thanks. This is very interesting. I'm just kind of trying to think through what happens when you have Arctic sea ice decline, because then presumably, you're exposing the open ocean water and it's warmer and the surface energy balance is completely different. On the other hand, you might be doing that in seasons of the year where the inversion isn't really much of a thing anyway.
Yeah, so sea ice decline is represented here by this change in Fs. So Fs is the surface absorbed solar radiation, and so as sea ice declines and the albedo decreases, that's going to increase, right? So this is what sea ice decline does as represented in this simple model, and it is the biggest term, right? I mean, that's it's not a true feedback in this model because I don't have an interactive sea ice component. So I've just I've prescribed some value of the change in Fs, which is 10 watts per square meter. But that's sort of, I took that value of 10 watts per square meter as something reasonable, within CMIP 6 for the strength of the sea ice albedo feedback. Okay, so sea ice albedo feedback does this, and it's the biggest component, the biggest driver of the near surface relaxation of the near surface reduction in the inversion strength. Okay, I'm not sure, you know, I mean, the other thing is, to what extent could these other terms lead to sea ice retreat, right? Is that what you were after, or?
Yeah, I mean, I'm trying to think of it in terms of feedback. But or is
Yeah.
it just that, you know, when the surface gets warm enough, then then you don't have a cooling fin at all, because it's easier to radiate energy out to space than it is to put it in the surface and get rid of it from the surface.
Yeah, that's right. So eventually the inversion will weaken so much that it will go away, right? And that will happen when, you know, in particular when this term gets big. I mean, it's most of the changes are near the surface are driven by this term. Okay, so if there's enough sea ice albedo feedback, you will lose the inversion. Okay, at which point, you know, you might even get convective instability and moist convection and so on, and in which case the surface energy balance will change completely. So then you would then transition into a different regime, which is what is being called radiative convective advective equilibrium, some sort of mixed regime,
Right.
which you have some convection, but lateral advection still plays a role.
I guess in this formulation, you're not taking into account the moistening of the surface atmosphere if you take away the sea ice, which I guess would also increase the opacity of the bottom atmosphere and make it easier to radiate out the top.
Yeah, so here I'm just taking Q as, so there is interactive water vapor feedback here. Okay, so I can, you know, so one thing I actually didn't mention is that in the full simulation, the water vapor is just constrained to be is constrained by keeping relative humidity constant in the column. Okay, and what I'm showing here is the response to the change in specific humidity driven by that constraint of constant relative humidity. Okay, and it's interesting that both, I mean, a sort of an interesting aspect of this work is that it provides an explanation for why the response to greenhouse gases is bottom amplified, right? Which it's been seen before in other column models in previous work that I mentioned by Cronin and Janssen and Henry et al. But, you know, it wasn't clear why that happens. And what we're saying here is that it's because of this. It's because the greenhouse gases reduce the ability of the surface to cool directly to space. Okay.
And so we're a little bit past the hour now, so we should probably thank our speakers one last time. So thanks to Lori and thanks to Rodrigo. Appreciate you coming to talk with us and show your work today. There's a couple more questions in the chat, so if the speakers could or wanted to stay longer, or folks wanted to stay longer, but otherwise, thanks, and I think we'll see you in the new year for the next iteration of this.
Thank you.
Thanks.
Thanks, guys.
And I'd be happy to follow up with anyone.
Matt, do we have to do anything to stop recording? Or have you done?
I am stopping recording right now.
You got the recording. Okay.
Yeah.